It is a usual practice in mathematics that once we learn about an object, we learn how to do operations on that object, and functions are no exception to that rule. The first operation we're going to learn on functions is called the addition of functions, and it follows very naturally from what you would think addition would be. So if you want, if you have two functions f and g, we can define the sum function f plus g of x to simply be f of x plus g of x for a given input x, okay? And the domain of the sum function is going to be basically the intersection of the domains of the two functions. For example, if we have f of x equals x squared plus 2 and g of x equals 5x minus 3, we can go ahead and look at f plus g of x, which is going to be x squared plus 2. It's just going to be, remember, f of x. Let's go ahead and start with that. So this is going to be f of x plus g of x. So now we substitute for f of x, x squared plus 2. And for g of x, we substitute 5x minus 3. And now, if possible, we go ahead and simplify that expression. And we end up with x squared plus 5x minus 1. Okay, so that is the result of applying the sum function for those two functions. Now, if we want f plus g at a specific input value like -1, we have a couple of options. We can actually go ahead, now that we know what f plus g of x is, we can just go ahead and substitute -1 in this expression that we found for f plus g of x and obtain our answer. So we would end up with quantity -1 squared plus 5 times quantity -1 minus 1. So we end up with 1 minus 5 minus 1, which is -5. So this is f plus g evaluated at input -1 using the expression we found for f plus g of x. Now we could have done this a different way. We could have just found f of -1 and g of -1 and added those, because look, we said f plus g, right, of x equals f of x plus g of x, right? So f plus g of -1 should just be f of -1 plus g of -1, right? So f of -1 is quantity -1 squared plus 2, so it's 1 plus 2, which is 3. Now g of -1 is going to be, we're going to substitute -1 for x in the expression for g. So 5 times -1 minus 3. So we get -5 minus 3, which is -8. So now all we have to do is add those. So we're looking for f of -1 plus g of -1. So we get 3 plus -8, which is just 3 minus 8, which is -5. Okay, so notice we get the same answer regardless of the approach. All right. Now notice that these are both polynomials, so their domains are the entire set of real numbers, right? So the domain of the sum function is also going to be the set of real numbers, because it's the intersection of the two domains, and what is R intersect R? That's just going to be R, right? All right, so here's a visual of what's going on here. So you're taking this function in red, right? Well, this is the graph of the function, of course, and this linear function in blue, and adding them, and what you end up with is this green function that you see here. So basically, graphically speaking, the parabolic shape is going to dominate. So your sum function is still going to be parabolic, right? And that's basically what we're looking at here with the sum function. Subtractions of functions is handled through what we call the difference function. So if you have two functions f and g, we can define the difference function of x to be just f of x minus g of x. And the domain is once again going to be the intersection of the two domains for the original functions. We have a typo here. All right, so I corrected it. I had written f plus g by mistake, so it's f minus g. F minus g is referred to as the difference function for f and g. So to find f minus g of x, we're basically going to just take f of x and subtract from it g of x. So f of x we know is x squared plus 2 minus, now if g of x has more than one term in it, you want to make sure you put parentheses after the minus sign, because the negative is going to have to be distributed like so, right? So we get x squared plus 2 minus 3x minus 5. So combining like terms, which are the constants, we get x squared minus 3x minus 3. Okay. So again, to find f minus g evaluated at -1, we can go ahead and plug in -1 here, because this is the expression for f minus g of x. So we get quantity -1 squared minus 3 times -1 minus 3. So 1 plus 3 minus 3, which is just 1. Or we could handle these separately and then subtract the two results. So f of -1 is going to be quantity -1 squared plus 2. So that's 1 plus 2, which is 3. And g of -1 is going to be 3 times -1 plus 5, right? Of course, we're just substituting -1 for x in the expression for g. So we get -3 plus 5, which is 2. So now we're going to subtract in this manner 3, which is f of -1, minus 2, which is g of -1, and we end up with 1. Notice again, of course, we get the same result no matter which approach we take. Domains, of course, once again, are the set of real numbers all around for the two functions, f and g, as well as for the difference function, which is just their intersection. Graphically speaking, here's what we're looking at. We have f, which is the red function, minus g, which is the blue function, the linear function, and the difference is depicted here in green. That's a graph of f minus g. Of course, notice at each x value, the y value of f minus g is going to be whatever y value you have for f at that point, minus whatever y value you have for g at that point. So that's basically all that's going on here. Okay, you can see that here with the three examples, right? So notice that you can get this -1 by taking the -1 for a g and subtracting from it, the y value. So take the y value for the red function, which is 3, subtract from it the y value for the blue function, which is 2, and you end up with 1, which is the y value for the green function. All right. And that will hold at every point in their domain, which is for all real numbers, right? And that's how the subtraction of functions is handled through the difference function. So one question that may arise is, which is better? Should we, if we're asked to find f minus g of -1, for example, Is it better that we approach it this way, you know, by finding f minus g of x first and then finding f minus g of -1, or should we do it directly like this by just finding f of -1 and g of -1 and subtracting them? Well, the answer is it depends. If you're asked to find f minus g of x to begin with, then it's better to just go ahead and use this method, just use the f minus g of x function. But if the problem simply asks you what is f minus g of -1, then you can just go approach it directly without having to go and find what f minus g of x is first. Next, we have the multiplication of functions as an operation. And if f and g are two functions, we define the product of f and g, or f times g of x, to be f of x times g of x. Again, with the domain of the product being the intersection of the two domains. Now, f times g is referred to as the product function for f and g. So here we're looking at the same two functions, but this time we're going to look at the product function. So f times g of x, by definition, is just going to be f of x times g of x, right? So, okay, I have no idea why these are disappearing. Let me investigate. I'll be right back. All right, I'm not sure exactly why the program was acting up, but I restarted it. It seems to be okay. We'll continue. All right, so f of x times g of x. Now, f of x is, of course, x squared plus 2. Given that it has more than one term, I'm going to parenthesize it. And the same with g of x. There's more than one term. We'll go ahead and use parentheses. So now we need to go ahead and just multiply this out. We'll distribute x squared first, then we'll multiply the 2 into the next group. Okay, so we get 5x cubed minus 3x squared plus 10x minus 6. So let's just double check. 5x cubed minus 3x squared plus 10x minus 6. And that's it. That is the product function. There's no simplification that's possible, so we stop there. So if we want f times g of -1, we have f times g of x, so we just plug in -1 for x, so 5 times quantity -1 cubed minus 3 times quantity -1 squared plus 10 times quantity -1 minus 6. So we end up with 5 times -1, because -1 cubed is just -1, so -5. Now -1 squared in the next term, that's just 1, so -3 times 1 is just -3. Positive 10 times -1, that's going to be minus 10, and then minus 6. So they're all negative, so we just need to go ahead and add them and keep the negative sign. So 8, 18, 24, -24. All right, now we'll go ahead and see if we can find that -24 without using the expression we found for f times g of x. So we're just going to say that f times g of -1 equals f of -1 times g of -1. Just go directly to the calculation of that particular functional value. So f of -1 is going to be quantity -1 squared plus 2, so that's 1 plus 2, which is 3. G of -1 is going to be 5 times -1 minus 3, so that's -5 minus 3, which is -8. So now we're going to multiply those two, and we end up with -24. So notice that if the problem is only asking you for f times g of -1, right, there's no need to go through all this work, right? You can just go directly to computing what f times g of -1 is. Okay, so but of course, if the problem is asking you for the general expression for f times g of x and you find it, then it's just quicker just to use that to get to your -24. All right, so as far as domain, both are polynomials with all reals as domain, and the intersection is R as well, okay? And that's multiplication of functions. And again, that the product function is referred to as, and f times g itself is referred to as the product function, okay? All right, next we want to take a look at division of functions. So we let f and g be two functions, and we define the quotient of f and g as follows. F over g of x equals f of x over g of x, with the domain of f over g being all x belonging to the intersection of the domains. And as you know, we always have an extra requirement when it comes to fractional situations, and that is we do not want the denominator to become 0. So basically, any x value in the intersection of the two domains that doesn't make the denominator function or the bottom function 0. F over g is referred to as the quotient function for f and g. So here we have our two familiar functions. This time we're going to find the quotient function. So f over g of x. As we know, that is going to be f of x over g of x. So it'll be x squared plus 2 over 5x minus 3. Now we want f over g evaluated at the input -1. So since we have f over g of x, we'll go ahead and plug it in. So we get quantity -1 squared plus 2 all over 5 times -1 minus 3. So we get 1 plus 2, which is 3 on the top, and -5 minus 3, which is -8 on the bottom. Normally, we like to put the negative sign on the side of a fraction, so we get -3/8. Okay, now what if we calculate it directly without having to go through all that? We can just figure those two out and then divide them to get f over g of -1. All right, so f of -1 is going to be -1 squared plus 2, which is 3. G of -1 is going to be 5 times -1 minus 3, which is -8. So of course, f of -1 divided by g of -1 is going to be again 3 over -8, which is -3/8. Okay. Now, visually speaking, this is what we're looking at. We're dividing the red function by, which is x squared plus 2, by the blue function here, which is representing this linear function. Now we can see the quotient function, kind of an interesting scenario. Now this is actually a two-piece function. There's another piece down here which I didn't have space for, okay, other than that piece. So because the place where this denominator becomes 0 splits this graph up into two parts, literally tears it up into two parts. Let me see if I can get you the whole graph. It's interesting enough to take our time for it. All right, before we go to the full graph, let's think of something as far as the domain is concerned. Notice that, as we know, the domain of both the numerator and the denominator of this fractional function is the set of real numbers. However, notice we have to exclude whatever number makes the denominator 0. Now, if we set 5x minus 3 equals to 0, of course, we get 5x equals 3, so x equals 3/5. So 3/5 is not in the domain of this particular fractional function or quotient function. Okay, here's the graph in its full glory. Notice that we're dividing the red function, right, by the blue function. Of course, we're referring to the graphs, you know what I mean, to obtain the green function, right? So, which is this one. Now, as you know, this function is undefined when x equals 3/5, and that exactly is what happens visually as you look at it. We have a vertical asymptote here. This green curve will never cross it. It almost looks like it's doing so here, but that's because of limitations of physical graphing. This will continuously get closer and closer, but it will never actually cross that line, okay? So notice that that's precisely at the point where the denominator becomes 0. So that's why we need to remove that as part of the domain of f over g, because it's not going to be in its domain. It's a point that you have to exclude from the domain. Remember, always remember, the domain, think of it as the set of allowable inputs, right? And here 3/5 would not be an allowable input. It is for this function, right? No problem. 3/5 causes no problem. It is for that function, because 3/5 doesn't cause any problem for that function. It's where the x-intercept. It's where it crosses the x-axis, right? So, however, when you divide the two functions, then 3/5 becomes problematic, because that's where this fraction would blow up. Okay. Now remember that visually also, for any point in the plane, of course, except 3/5, because that we don't even consider. If you take the y value or the functional value evaluated at that x value and divided by the g value at that point, then you should get the same thing that you would get from this function. That's what the quotient function basically is. Okay, so let's go ahead and move on. All right, so whereas the domains that we've seen so far have all been the real numbers, here we're going to need to say are, but not elements of this set, which is basically only a set containing the number 3/5. And in in interval notation, you can say negative infinity, comma 3/5, union 3/5, comma infinity. That looks a little bit like a period. Let's make it a comma, okay? So there we have it. That's the quotient function. Always, when it comes to division, you have to be a little bit more careful than you are with our other operations because of the restrictions involved, right? Not more difficult, just requires more attention. All right, in this next example, we're going to use this graph to see if we can come up with these values, if possible, okay? So for the first one, see if you can, try it yourself and come up with it. It's kind of fun to work something out without any help and then come back. All right, so we have f plus g of 4. Now, as we can see on the graph, f is the linear function and g is the function that looks kind of like the square root function, right? At this point, you should be familiar with these shapes. You want to become very, very familiar with the shapes of the functions that I've been referring to as commonly encountered functions, right? All right, so by definition, we know that's going to be f of 4 plus g of 4, right? So according to this graph, when the input is 4, we go all the way, we go straight up till we hit the graph of f, and then go straight left till we find what the output is. And we can see the output would be 9. So because 4, 9 is a point on this graph, right? That's 4, 9. But remember, you can also think of it as 4 comma f of 4, see? So the y value is where we where we pick the output values from, right? So the input is x and the output is f of x. So each point on the graph of a function can be thought of as x comma f of x, like that, right? All right, so f of 4 is 9. For g of 4, we look at the function g. When the input is 4, we go all the way up and then immediately to the left, and we see that it's at 2. So it does look like that is the square root function, doesn't it? The square root of 4 is indeed what? 2. So we get 9 plus 2, which is 11. Okay? How about f minus g of negative 2? Well, by definition, that's going to be f of negative 2 minus g of negative 2, right? So we go to the input negative 2. To get to f, we have to go straight down, all right? And then we'll go straight right this time, right? Till we hit negative 3. So that's going to be f of negative 2. And then minus, what is g of negative 2? Well, g is only defined for what? Is only defined for non-negative numbers. So g of negative 2 is what? Is undefined, right? So therefore, this whole thing will be undefined. Because what is negative 3 minus some undefined number? Well, we don't know. That's also undefined, right? So therefore, this one is not possible to calculate, right? All right. How about f times g of 1? We usually don't even put a dot between them when it's multiplication. So we can just put fg, just like we do with variables or, variables. With numbers, we usually put them because we don't want to mistake 2 times 3 with 23, right? So we should use dots. But when we're dealing with like x and y variables, etc., we don't usually put a dot even, right, when we multiply. So we get f times g of 1. By definition, that's f of 1 times g of 1, right? Now, f of 1, so we go to x equals 1, go straight up till we hit the function f, and then go left. So we can see that's at 3 times g of 1. Now g, we start at input 1, go up, and then left till we see where it hits the y-axis, and that's 1. So 3 times 1, that's going to be 3. How about f over g of 0? Well, we know that by definition, that's f of 0 over g of 0, right? Now, f of 0 is, we start at 0 and go up, right? So that's going to be to see where we hit the line, and that's at 1, right? So f of 0 is 1. How about g of 0? Well, g of 0 is right there. It's 0, right? G goes through the point 0, 0. So the function evaluated at 0 is 0. Think about it. If g is in fact square root of x, what is g of 0, right? It's the square root of 0, which is 0, right? So it makes sense. So that's 1 over 0. So this is what? This is also undefined, okay? So we had 2 undefined results and 2 well-defined results, okay? And that's how you would approach something like that. All right, next we want to take a look at the important concept of composition of functions. All right, sometimes it's necessary to use the output of one function as the input of another function. Processes involving such sequential functional operations are called iterative processes. All right, one beautiful example of iteration is the process that generates what's known as the magnificent Mandelbrot set. Well, without the magnificent, but that's just my opinion. There is a whole lot of complexity to this picture. So there is a lot more to the picture than just being beautiful. For example, one of the neatest things about it is that it has clearly a finite area, okay, because you can, encircle it within a circle which is not very large, and the area would be fully contained in it. However, if you try to calculate the perimeter of this extremely complex figure, then you would reach infinity. It would be an infinite perimeter. So anyway, just iterative processes are really amazing processes. So but we're not really getting into anything like this. Just thought it would be interesting for you to see an example of some of the things that we talk about. All right, so here's a more down-to-earth example. Let's say that you go to a clothing store in the middle of a major promotional event, and you find that your favorite jacket costs $100, and it is sitting on a rack above which is written 30% off every item on this rack. Now, at the door, it's written an additional 20% off already reduced prices, right? At the register at the time of checkout. So how much will you end up paying for your favorite jacket, which was originally marked $100, basically? So many people who read this seemingly simple problem get the wrong answer. That's because they do not know about the composition of functions and iterative processes. Most people who read this problem assume that they should only have to pay $50 for the originally $100 jacket, because they reason that, look, 30% of 100 plus 20% of 100, that's 50% of 100, so that's what? 50. This, however, is not the right way, and this, which we're going to show you now, is the correct way of dealing with it. First, you must deduct the 30% from the $100, right? So what's $100 minus 30% of $100? That's going to be 100 minus 30, which is 70, right? Now you must take 20% off this amount, okay? The common error is to deduct 20% from the original 100, you see? So that's what people, that's where the main mistake occurs, right? So 70 minus 20% of 70 is going to be 70 minus 14, which is 56. So you actually end up paying $56 plus taxes, of course, and not $50. And this is where people may get upset at the register. Hey, you said this and that. But really, if you just do the simple math, you will realize that the cashier is correct in this case. All right, so where does this fit into our composition of functions, which we're about to define? So let's get there. As it turns out, we can solve this problem using two functions. We define the first function as the price after 30% discount function. So f of x is what? So when you reduce something by 30%, you actually have to pay 70%, right? So the first function we define is f of x equals 70% of x, where x is the price of the item, right? So if you simplify it, 70% is the same as 0.7x. Note that f of x here calculates the price after a 30% discount. Now, we define the second function as the price after 20% discount function. So this time that means our g of x, our second function, is only going to be 80% x, right? Which is the same as 0.8x, because when you get a 20% discount, that means you're going to pay 80% of what the original price was, right? For any check at the register totaling x dollars. Now we could get the answer to the question that we had on the previous page using one clever functional evaluation. Basically, we first apply f to the original price, which was 100, right? Then we apply the function g, which is the 20% off function, to the output of f, right? Notice that the output of f, the first function, becomes the input of the second function. So we get g of, now what is f of 100? Well, Here's f of x. It's 0.7 times x. So f of 100 is just going to be 0.7 times 100, right? So we get g of 0.7 times 100, which is just g of 70. And what is g of x? It's 0.8x. So we just take 70 and plug it in, and we get what? 56. So we were able to handle all of that very quickly and efficiently using a couple of functions with an iterative process where the input was used as the output of the next operation, right? Of course, with something like the Mandelbrot set, this happens over and over and over again, right? Here we only have to do it one time. This type of functional evaluation, where the output of one function becomes the input of another function, is called the composition of the two functions. We formally define the composition of two functions as follows. Let f and g be two functions. The composition of f and g, called the composite function, is given by this notation: f circle g of x. Make sure that this is left as an open circle. You don't want to mistake this with multiplication symbol. So when you write it with a pen, you have to make sure you make a nice open circle, okay? Times g of x, which is basically none other than f of g of x. So in other words, evaluating f by using g as the input, right, for any given input of g. Now, the domain of f circle g, or the domain of the composite function, is going to be any input that is in the domain of g such that g of x belongs to the domain of f. Now, sounds like a little bit confusing, but it's not. So remember, the domain of the composite is never larger than the domain of the what? The second function, the g of x, right? And even those, you can only accept the ones which don't cause any problem for the f function, right? So again, look at that for a while and convince yourself that that makes sense to you, because it's important to be able to do simple analysis like this and understand it. And this does make sense, because remember, you're going to be calculating f of g of x. So that means this entire function has to make sense, right? Firstly, so x has to be in the domain of g to begin with, for g of x to make sense. And then we have one other restriction, is that g of x itself should be in the domain of f, okay? In general, the composition of two functions is not commutative. So what does that mean? That means direction matters. F circle g is not usually the same as g circle f. It does happen to be so for like at least one very special group of functions, which are reversible one-to-one functions that have an inverse. A function and its inverse will satisfy this. So f circle f inverse equals f inverse circle f, and both of them will give you the original input x, but not in general. In general, we do not find this to be true, right? I mean, we find this to be true, meaning that it's not commutative. In other words, f circle g usually results in a different expression from g circle f. All right, so here we have two functions, f of x equals 3x minus 1 and g of x equals 3 over x minus 1. We want to go ahead and find f circle g of 1 and g circle f of 1. All right, so you should probably try it on your own first and then see if we agree. Now, f circle g of 1 basically by definition means f of g of 1, right? So that's f of 3 over 1 minus 1. We know this is 0, so this becomes what? Undefined. Therefore, this is going to be undefined, okay? Now, this doesn't necessarily happen with G circle f of 1. So don't automatically assume that's going to happen. So G circle f of 1 is going to be G of f of 1 by definition. So that's G of, now we're going to figure out f of 1. F of x is 3x minus 1, so f of 1 is going to be 3 times 1 minus 1. That's 3 minus 1, which is 2, so that's going to be G of 2. Now, what does G do to an input? It takes 3 and divides it by that input minus 1. So it's going to be 3 over 2 minus 1, which is 3 over 1, which is 3. So notice that G circle f of 1 was well defined, but f circle G of 1 was not well defined. It was undefined, okay? So you can clearly see f circle G and G circle f don't always produce the same result, right? All right, so make sure you understand that and we'll proceed. So, okay, here we have two functions, f of x equals square root of x minus 5 and g of x equals 7x. We want to find f circle G and G circle f and their domains. Keep in mind that the domain of f circle G is all x belonging to the domain of G such that G of x belongs to domain of f. Okay, so let's go ahead and find f circle G. Now, f circle G of x by definition means f of G of x, right? So that means f of what? What is G of x? G of x is 7x, right? Now, so we want to evaluate f, but use 7x for input instead of x. So that means wherever you see x in the definition of f of x, replace it with 7x. So that's going to be the square root of 7x minus 5. All right, so as far as finding the domain, we need to find the domain of f. We know that that's for f, remember f is a radical expression, so we want x minus 5 to be greater than or equal to 0. So we want x to be greater than or equal to 5. So the domain of f is bracket 5 comma infinity, right? Now g, of course, is just a polynomial, so in fact a linear function. So the domain of g is all reals, right? Now, however, when we look at the composite function, we can clearly see that there's going to be a restriction because it's a square root function and this needs to be non-negative, right? So we want 7x minus 5 to be greater than or equal to 0. So 7x should be greater than or equal to 5. So x should be greater than or equal to 5/7. All right, so as long as the numbers in the region from negative infinity, actually 5/7 comma positive infinity, as long as they are in the domain of G, which they are, right? G is all real numbers, right? And as long as we apply the function G to them and they remain part of the domain of f, we should be okay. Now, notice that if you multiply 7 by members of this group, right? Notice 7x is going to be greater than or equal to 5/7 times 7. So that means x is going to end up being greater than or equal to 5, which of course satisfies the domain of f. So this group right here is, here we need a bracket, right? Not a parenthesis. So the domain of f circle g is going to be bracket 5, 7, comma, infinity. All right. All right, next we're going to take a look at this problem where f of x equals the square root of x minus 5 and g of x equals 7x. We want to find f circle g, g circle f, and their domains. And here's a reminder of what the domain of f circle g, for instance, should look like. It should be all x in the domain of g, such that g of x belongs to the domain of f. So for f circle g, we know that f circle g of x, or f composed g of x, is going to be f of g of x, right? So that means f of, now we know g of x is equal to 7x. All right, so what does f do to an input? It takes the square root of that input minus 5. So we're going to replace the input x with 7x, right? So we get the square root of 7x minus 5. Now, we know that the domain of f, because it's a square root, is going to have to be all numbers that keep this non-negative. In other words, we want x minus 5 to be greater than or equal to 0. So we want x to be greater than or equal to 5. So the domain of f is going to be bracket 5, comma, infinity, right? The domain of g is all reals because g is just a simple polynomial function, right? So as far as the domain of f circle g of x is concerned, we notice that there's a square root, so the radicand needs to be what? Needs to be non-negative, so we want 7x minus 5 to be greater than or equal to 0, so 7x to be greater than or equal to 5, so x to be greater than or equal to 5/7. All right, now, so as long as this group is in the domain of g, which it is, right? And as long as applying the function g to it, which is multiplying whatever input by 7, keeps it in the domain of f, we should be good to go, right? And notice that this group is within the domain of g because the domain of g is all real numbers. And if you apply 7 to these numbers, you'll end up with 7x greater than or equal to 5. We already saw that. And that is going to satisfy the need for the function f of x to remain well defined. So this group is indeed going to be the domain of f circle g. So bracket 5/7, comma, infinity. All right, for g circle f of x, that's going to be g of f of x. So it's going to be g of square root of x minus 5. So we want to compute g with this input, right? This expression as the input. Now, what does g do to an input? It multiplies it by 7, right? So there it is. That's g circle f of x. All right, so we can see the expression for g circle f contains a radical, so we know that the radicand must be non-negative, so x minus 5 must be greater than or equal to 0. So x has to be greater than or equal to 5. All right, so this is the domain of g circle f, so it should be all x belonging to the domain of f, right? This has to be switched around. So see, the domain of g circle f is going to be all x belonging to the domain of f, such that f of x belongs to the domain of G. And of course, given that the domain of G is all reals, we should be good to go with this restriction itself. So we get the domain of G circle F equals bracket 5 comma infinity. All right, so there we have a couple of composition problems. Make sure you can handle these simple problems and we'll proceed. All right, so here we have another problem that we're going to look at. F of x equals 1 over x minus 3 and g of x equals 2 over x. We want to find the compositions in both directions and then their domains. So go ahead and see if you can do this on your own first and then come back. All right, so we know that f circle g of x is going to be f of g of x. So that means f of 2 over x. So we're going to apply the function f to this input. So wherever we see x in the expression for f, we're going to replace it with 2 over x. So we get 1 over 2 over x minus 3. So the fastest way to simplify that is to go ahead and multiply top and bottom by the LCD of all the fractions that you see. There's only one with a denominator of x, so we're going to do that. So we're going to multiply the numerator and the denominator of the complex fraction by x. All right, so notice that we end up with x over, here when you multiply x by 2 over x, the x's cancel out, so we get 2 minus 3x. Okay, so there's the expression for f circle g of x. So we're going to look for the domain now, which is going to be all the numbers in the domain of G, so that the G of x is going to be in the domain of f. So basically, look for any numbers that should be excluded because of the G itself, which would be 0, right? So x can't be 0 because x is 0 is not in the domain of G, right? So x shouldn't be 0. Also exclude any numbers that would cause you problems here, right? So we don't want this denominator to become 0 either. So go ahead and include those. So 2 minus 3x equals 0. If we solve that, we get 2 equals 3x. So x equals 2/3. All right. So basically, you want all real numbers except those two numbers, right? If you take a look at the number line, basically, you want these two numbers, 0 and 2/3, removed. So basically, you want everything from negative infinity to 0, union everything between 0 and 2/3, union everything after 2/3. There you go. And that's the domain of f circle G. Note that it's really important to check the domain of G, because notice 0 doesn't cause any problems for this particular denominator. 0 doesn't make this denominator 0. So if you're only looking at this and trying to determine what values of x would cause a problem with this expression, you would have missed the 0. That's why you have to remember, to be in the domain of f circle g, you have to be in the domain of g to begin with, right? So there is no way 0 can be in the domain of f circle g because of the fact that it is not in the domain of g, okay? So when you want to find the domain of f circle g, yeah, look at the expression for f circle g, exclude any numbers that are problematic, but also look at the domain of g and make sure that you're not including any numbers that are not in the domain of g, okay? All right, we'll look at g circle f now. All right, so we get g of f of x, which is g of 1 over x minus 3. So basically, we get, remember, we're going to apply g to this input, right? So wherever we see x in the expression for g, we're going to replace it with 1 over x minus 3. So we get 2 over 1 over x minus 3. So that just means 2 divided by 1 over x minus 3, which is 2 times x minus 3 over 1, right? Just definition of division of fractions, right? So 2x minus 6. All right, so g circle f itself ended up to be a nice, being a nice simple polynomial function, right? No restrictions. However, remember, take this and write the g circle f version of it, and you end up with domain of g circle f equals all x belonging to the domain of f such that f of x belongs to the domain of g, right? Things get turned around. So in order to be in the domain of g circle f, you have to first and foremost be in the domain of f. So notice 3 itself is not in the domain of f because 3 makes f undefined. So we cannot use 3 in the domain of g circle f either. So given that that's the only problem causing number, so we want x not to be equal to 3. So the domain of g circle f is going to be basically all real numbers except 3. When you look at it on a number line, you're just going to have a gap at 3. So we're going to have negative infinity to 3 union 3 to infinity, like so. Okay? Again, a little bit more complex than regular domains and ranges that we look for, but if you just think about it a little bit, it'll start to click and make sense. You just have to pay attention to the nuances, right? And that's what growing is all about, right? Increasingly paying attention to nuances. All right, let's go ahead and proceed. One quotient that you will encounter quite often in a calculus class is called the difference quotient. And what it is basically is it's the slope of the secant line going through these 2 points for this graph of this function f of x. We already defined the secant line in a previous video to be a line that crosses a curve at least 2 points. Now this one, for example, is crossing at 3 points. So if you think about the slope of the line going through these 2 points, you would know that we can think of like the first ordered pair x f of x as x1, y1, and this other ordered pair as x2, y2. Notice that if this is the point x, then this ordered pair is going to be x comma f of x, right? And if this is x plus h, the point on the graph here is going to be x plus h comma f of x plus h. Now we're going to find the slope using the slope formula. So y2 minus y1, that's f of x plus h minus f of x over x2 minus x1. So x plus h minus x. Of course, the x's cancel out, leaving us just what? H. That's why we only have h down below. So this right here, this difference quotient, is nothing but the slope of the secant line for the graph of a function going through the points x f of x and x plus h f of x plus h. Now we'll go ahead and actually find the difference quotient for a few examples. All right, so here we have the function f of x equals 3x squared minus 4x, and we want to find and simplify the difference quotient for f. So you have to keep in mind that the difference quotient is f of x plus h minus f of x over h. So we have, now remember that f has the action on an input that it squares it, multiplies it by 3, and then subtracts 4 times that input. So now we're going to apply that action to x plus h, right? So wherever you see x in the definition of f, simply replace it with x plus h. So we get 3 times quantity x plus h squared minus 4 times quantity x plus h. And all that we just wrote is just f of x plus h. So we still need to do minus f of x, right? So minus, now f of x is just that, right? So we just make sure we use parentheses because it contains more than one term, f of x. So we get 3x squared minus 4x in parentheses, and on the bottom we have an h. So now we go ahead and work this out using the formula we just learned. So we get x squared plus 2xh plus h squared, right? Let's go ahead and distribute the minus 4, the negative 4, so we get negative 4x minus 4h. We're going to distribute this negative 1 here, invisible 1, so we get minus 3x squared plus 4x all over h, right? So let's go ahead and distribute the 3, so we get 3x squared plus 6xh plus 3h squared minus 4x minus 4h minus 3x squared plus 4x all over h. Now, we notice some cancellations. I noticed the 3x squared here cancels that negative 3x squared, and the negative 4x and 4x cancel out as well. So we're left with 6xh plus 3h squared minus 4h all over h. So since we're asked to simplify, we'll go ahead and factor h. Seems to be a common factor to all 4 terms involved here. So we get h times 6x plus 3h minus 4 over h. So finally we get 6x, because the h's will cancel out now, right? Plus 3h minus 4. Okay, so there is the difference quotient for this particular function. Again, it's not difficult, it's just a little bit tedious is what you would call it. There's a difference between difficult and tedious. Tedious, there's a lot of details, etc., but not really difficult as far as concepts are concerned. So just be patient and you'll be fine. All right, let's go ahead and look at one more. All right, so this time our function is the good old square root of x, and we want to find the difference quotient for it, okay? So remember that difference quotient is basically the same regardless of the function, which is what? F of x plus h minus f of x over h. You're finding the slope of the secant line for a general point x, and the corresponding point on the graph of the function, and a point a little bit later, x plus h, and the corresponding point on the graph. So here we have, now f of x is square root of x. So what is f of x plus h? Wherever you see x, replace it with x plus h. So it's just square root of x plus h, right? Minus f of x. All right, I'm not going to need fraction line that big. Let me make it smaller. And then over h. Now, you're used to rationalizing the denominator, right? Well, there's a trick which uses the same kind of technique, but for rationalizing the numerator, which sometimes ends up helping us simplify. So that's what we're going to use here. We're going to multiply the top and bottom of this fraction by the conjugate of the denominator. So square root of x plus h plus square root of x over the square root of x plus h plus square root of x. In other words, by the same thing. Remember, all we're doing is we're multiplying by 1, because top and bottom of this fraction are the same, so the actual value is 1. Now, on the top, if you recall, if you have f plus l times f minus l, that equals what? F squared minus l squared, right? So therefore, we're going to get, think of this as f and this as l, right? So we're going to get f squared minus l squared, which is square root of x squared, over h times square root of x plus h plus square root of x. So on the top, we end up with x plus h minus x, right? Over h times square root of x plus h plus square root of x, right? So notice the x's will cancel out. You end up with h over h times square root of x plus h plus square root of x. The h's will now cancel, leaving us 1 on the top, and square root of x plus h plus square root of x on the bottom. All right, so there's the difference quotient for that one. All right, that pretty much brings us to the end of what we're going to do. So we're just going to do a quick recap and then call it the day. All right, one quick warning before we do the recap. And that is the fact that f of x plus h, you got to be careful. That is not the same as f of x plus f of h. You can easily verify this on this function, for example. Go ahead and try to do it as a great practice for you. Find f of x plus h, and then add f of x to f of h, and you can verify that they're not the same. Okay, so I'll leave that for you as a practice problem. Okay, now just to summarize, here are the functions that we learned about today. We learned about the sum function. All of these, of course, depend on the fact that we have two functions, f and g, right? So the sum function is just f plus g of x, which gives us f of x plus g of x, with the domain being the intersection of the two domains. Then you have the difference function, which is just f minus g of x, which is f of x minus g of x. Again, the domain of f minus g being the intersection of the domains. And then the product function, just as you would expect it to be. The quotient function is the first place where you have to be a little careful with the domain, because you do not want to allow the denominator function to become 0. So you specify that g of x should not be 0. And the composite function, also you have to be careful with the domain, because the domain of a composite is x belonging to the domain of g, such that g of x belongs to the domain of f. All right, so that should kind of do it for today. So you take care of yourself until we see you at the next one.